Hello everyone, Greg is here. Happy New Year. Thank you for everyone subscribed to this channel. Very glad to see that even when I'm not posting anything, I still get new subscribers. Promise to improve next year with more videos. Today I want to cover this question on the top. Can frustrated radical pairs react like frustrated Lewis pairs? And I'll show some results of the quantum mechanical calculations, DFT calculations, that I did with a collaborator. Let me first remind you how frustrated Lewis pairs react. So here is the typical reaction of the frustrated Lewis pair, which is composed of a phosphine and a borane. And the reaction is with the hydrogen, in which the pair splits the dihydrogen. The idea of frustration, I remind you, is that the groups that sit on the central atoms, on the phosphorus here and boron here, are very big, and they do not let the bond between them form. So if though there was no such big groups, there would be just phosphorus boron bond and that's it. But when this bond cannot form and there is a space between the two atoms for a dihydrogen or another molecule to enter, something happens and the molecule is steered apart. And dihydrogen is not a very reactive molecule. The reaction was discovered by Professor Doug Stefan in 2006. The mechanism was first proposed and proven to some extent in 2008 by Professor Papai. In 2023, the group of Professor Chalasinski from Poland, they showed that before dihydrogen enters the space between the two molecules, they don't really interact, not between the central atoms at least. There is some dispersion interactions, van der Waals bonds between the groups, but there's no exchange or any quantum effects between the atoms. But when the dihydrogen enters this cavity, it acts as a relay and electrons jump from phosphorus to the hydrogen and from the hydrogen to boron, and the bond here splits. So I was always curious to understand maybe some other molecules can react the same way, because it's pretty unique. And by other molecules, I mean radicals. Okay, so can two frustrated radicals react with the hydrogen or another molecule in the same way, in the concerted manner? Well, the current knowledge base actually shows that frustrated radicals react in a very different manner. So while the reaction here is concerted, it's all three molecules react simultaneously. With radicals, the reaction is stepwise. First, one radical reacts with one part of the molecule. In this case, it's not the hydrogen, it actually reacts with carbon-hydrogen bond. So first, one radical obstructs the hydrogen, and then the second hydrogen captures the radical that remained. So the reaction is stepwise. Can it be not stepwise? Can it be concerted? So I have two ideas how it can happen. Idea number one, that can be an electron transfer between the two radicals in the pair. Basically, they will form a frustrated Lewis pair, which will react. This idea was not really studied anywhere, from what I know. Usually it's the opposite. When you take a frustrated Lewis pair and you have an electron transfer and you get two radicals, but not when you have two radicals and you have electron transfer and you get Lewis acid and Lewis base. But actually, you can find such reactions in the literature. This was my publication from 2009. We had such reaction, though we had no idea back then about the FLP concept or FRP concept. It was brand new then, and we didn't call those steps FRP or FLP or anything like that. So we irradiated this stable silicon centered radical, and it reacted to obstruct hydrogen from another radical molecule, and we showed by some DFT calculations that likely that what happens. You have a formation of frustrated Lewis pair. Anyway, this idea is nice, and if by chance you have stable radicals in your possession, you can try studying this one. But I also have another idea. If we go back to the original reaction, the radical pairs, as it currently described in the literature, no one really puts any attention on the spins of those radicals, and I'll explain why it's important. So if those radicals really do not depend on each other, don't interact between each other and their spins are not correlated, in this case, obviously the reaction will not be concerted. So because here in the dihydrogen, the spins are correlated, and in order for the second radical to react as well, this spin should be inversed, because on the orbital you need to have electrons with opposite spins. But what if these two radicals in the pair are correlated? If they're in singlet ground state, if the radical pair is in singlet ground state, in this case, this reaction can be concerted, can be simultaneous, like with FLP. In theory, you can ask me, well, how come the spins would be correlated? Why would they? Well, actually, in the literature, there's many examples in which two radicals which are not connected through bonds, like here or here, the ground state is a singlet ground state. If you look at this molecule, for example, the distance here is 15 angstrom and it's still singlet ground state. So those spins are correlated. When I was searching the literature, I saw that in biology it's actually a known phenomenon, and spin correlated radical pairs are used, for example, in the navigation system of birds that fly from north to south and back. It helps them with navigation with magnetic field. I will not go deep into this, but spin correlated radicals is a real thing. They also, in other publications, they're also called entangled radical pairs. So basically their spins are entangled, which is the same as correlated. I like the entangled more. It sounds more cool if you ask me. But anyway, so we can see that in theory, the radicals can be spin correlated or entangled, and that means, again, in theory, this reaction can happen as it's drawn here. And I wanted to do some quantum mechanical calculations to show, is it possible? Now, and we did so, and I'll show some results in a minute. I can tell you it didn't go very easy. It was pretty hard to get models of molecules that would provide results that make sense. It was very hard to optimize molecules. It was hard to choose the basis set that would lead to optimized molecules. But in the end, we had some very cool results. I will not show all of them. I'll show probably the most interesting one. By the most interesting one, I mean this one below. So it's not just split of the dihydrogen, although this one we also studied. Got some good stuff there. Why I chose this reaction? Well, first of all, if this reaction really happens, this is a big deal for chemistry in general. It's two carbon-hydrogen bond activation simultaneously. So from ethane you get ethylene. Another reason I wanted to study this reaction is because I actually think that this reaction happened in one of my projects, but we couldn't prove it at the time and we didn't think about this idea at the time. So I have some personal this reaction is personally important to me, and this is the model of the radical that we showed in our previous studies, that it only reacts with hydrogen abstraction. It cannot dimerize because it's too big, so it's frustrated. It doesn't have any side group reaction. Anyway, this model was very promising, so that's the one that we calculated here. First of all, we calculated what would be a singlet triplet gap. This is the triplet, and this is the singlet model. And the energy gap here was not that huge. 33 kilocalories per mole requires just mild heat. Now, let me tell you also a few words about this basis set that was used for the calculation. I know that this is not a very good one. What do I mean not a very good one? So onium only focuses on on the central atoms, on the skeleton, and cannot take into account the interaction between the side groups. So we're working on doing the calculations on a better one. You can see here a very beautiful highest occupied molecular orbital of the singlet. You can see that the molecule already interconnected. With triplet, you don't see any interconnection. That's the reactants. Then we calculated the transition state. In triplet state, only one of the radicals started to react with the carbon-hydrogen bond. The other one stepped aside. There is no simultaneous reaction of both radicals. With a singlet, however, you can see that two hydrogens are abstracted simultaneously. And you can see here that the pi bonding forms on the carbon-carbon double bond. And here is the calculation of the reaction energy. From triplet to singlet, you have 33 kilocalories. The energy gap between the reactants and the transition state is even smaller, which is very beautiful and again a bit unexpected. Overall energy of the reaction is minus 14.9 kilocalories per mole. So it's definitely thermodynamically viable, and it can happen even at room temperature, like it happened here. I think those results are very cool. We'll keep working on that. It still doesn't mean that this reaction really works as it's shown. It requires more experimental proof and better calculations as well. But I think it is for sure a proof of concept that the idea of FRP reacting like FLP in a concerted manner is not a fantasy, that it has ground. And with time, I hope we'll be able to prove it beyond reasonable doubt. Let me know if you have any questions in the comments. Please support Ukraine. Happy New Year. Have a nice day.